So today we'll start chapter 8. So chapter 8 is about pressure vessels. In chapter 8 we'll talk about members where you will have stresses because of uh, a force due to pressure. So these are special members. So we have already talked about axial forces, shear forces, bending moments, and we have talked about different loading conditions. But this chapter talks about a special loading condition, and this special loading condition is because of the pressure. So because of pressure, you will have some stresses in a member, and these stresses are called axial stresses and hoop stresses. So this chapter is a relatively smaller chapter. We can finish today, and then from next Wednesday we have exam, and after that we'll start Mohr circle. And Mohr circle is also one of the important and crucial topic in mechanics of material, which we'll start next time. So we can talk about pressure vessels today. So I'm gonna give you examples for pressure vessels, what pressure vessels are. So today's topic is about pressure vessels. So I'm gonna give you some examples. So for example, if you talk about soda bottle, this is a soda bottle. So if you talk about soda bottle, in soda bottle you have a gas, right? A carbonated gas, and this gas is actually applying some kind of a force onto the soda bottle container, right? So this is going to apply a force, but this force which is generating in a soda bottle, which is being applied on a can, is because of the pressure inside the soda bottle, right? So this force is being applied because of the pressure difference which we have from outside as compared to the inside of a soda bottle. Similarly, we have some other members as well. So, for example, if we want to talk about the pipelines, so this is one of the section of a pipeline. So, pipelines are also special members which carry liquid and gas. So, for example, it's carrying gasoline or pressurized gas. So, this pressurized gas is also because of the pressure, it's gonna apply the forces on the pipelines. And I can also give you another example. So, for example, uh, gas cylinders. So, people use gas cylinders also. So, in gas cylinder, you also have a pressurized gas inside, and this pressurized gas is also gonna apply external loads onto the walls of a cylinder. So this is a gas cylinder. So in all of these examples, you have a pressurized gas, and this pressurized gas is acting as an external load in this case. So in soda bottle also, in pipelines also, in gas cylinders also, you have a pressurized gas which is acting as an external load, and this pressurized gas is going to apply a force onto the container where it's enclosed, and because of these external loads you're going to have stresses, and you're going to have two type of stresses. You're going to have axial stresses, which we already know, and there's going to be additional stress because of the pressurized vessels, and this gas stress is called hoop stress. So this is a special case wherever you have a pressurized gas which is acting as an external load, and this external load is going to cause two type of stresses which are called axial stresses and hoop stresses. And this scenario, these type of members are called pressure vessels. So we're going to talk about these scenarios in this chapter. So whenever you have a pressurized gas inside a container, then this type of a situation is called pressure vessels, which is our chapter 8. So what we're gonna do is that we're gonna develop the equations for axial stresses and hoop stresses, and we're gonna use those equations to solve our problems of pressure vessels. So let's try to imagine what these axial and hoop stresses are. So whenever we are calculating stresses, we need to know the internal loads, right? So internal loads we can extract by making a cross section. So I'm gonna cut a cross section, and I'll try to expose the internal loads and the internal stresses. So if you make a cross section, I'm gonna draw half of the cross section here. So this is a gas cylinder. We have made a cut, and this is the pressurized gas which is acting as an external load. So this is pressurized gas, right? So this is gonna act as, let's just say, external loads. So these are like external loads. It's gonna be everywhere, but right now we're talking about the longitudinal. And as a result, we're gonna have uh, internal loads and the internal stresses. This kind of internal stress is called axial stress. And also, I'm gonna draw the cross section of this thing here. So if you cut a section and if you try to see from the top, that's what it's gonna look like. So I'm gonna draw a cross section of this pressurized pressure vessel here. So this is a cross section. It will have some thickness. So it will have some thickness T, but let's draw thickness a bit later. So these are the external loads due to the pressurized gas inside. So like here, this is a longitudinal load, but this gas is actually applying pressure everywhere. So if you look from the top, this gas will also apply an external load in this direction as well. Because this is a pressurized gas, it's gonna apply external loads everywhere. So this is one direction, and if you look from the top, this is another direction where the loads are being applied because of the pressurized gas inside. And this loading condition will also generate a special kind of a stress, which is going to be along the circumference. So if I draw the, so you're going to have a circumferential stresses as well. So it's going to be along the circumference. So because of these external loads, so this is going to try to like push everything outside. So because of this push, you're gonna have additional stresses inside, which are called hoop stresses. And this is only special for the pressure vessels. So this we already know. I mean, axial stresses, whenever you have along the axis, whenever you have a force, internal load, because of those internal loads, you're gonna have stresses which are called axial stresses. So this is along the axis. I can draw a member for you guys to visualize. So we already know whenever you have a member and this is axis, this is called longitudinal axis, right? This is called longitudinal axis. So along the longitudinal axis, whenever you have a force, this force is called axial force. Sometimes it's also a normal force because this is perpendicular to the cross section, but the idea is the same. You just like make it like this, and then these are those axial forces and axial stresses. But in pressure vessels, you have a special stress which is called hoop stress. Now we're gonna just formulate the equations for the axial stresses and the hoop stresses which we'll use for the pressure vessels. So we can develop the equations by using equilibrium equations. So we're going to use equilibrium equations to formulate the equations. So basically we're going to use summation of forces is equal to 0. So in this case, we can see that there is a force because of the pressure minus you have a force, internal force, which is, I'm going to say axial force. And we can just, that's going to be equal to 0. This is force, so stress is force per unit area, pressure is also force per unit area, but the areas are different in this case. So from this we can calculate forces. So forces is going to be stress into area. This is also going to be, this is going to be, this is pressure, so this is going to be pressure into area. This is going to be stress into area. But I'm just gonna skip the derivation and I'm gonna just write the final equation for the axial stress. So this is basically axial stress. So if you do the derivation, area is pi r square, this area is also pi r square. So if you do the derivation, you're gonna get axial stress as P, this P, and R over 2T. This is our equation for the axial stress in the situation, in a pressure vessel situation. So this is the formula for the axial stress. So if you do the derivation for hoop stress, you're going to get the formula for hoop stress as PR over T. So in a situation where you have, where you can call a member as a pressure vessel, then you can calculate the axial stresses using this formula, and you can calculate the hoop stresses using this formula. So it looks similar, but you can conclude from this is that the axial stresses are half of the hoop stresses. So in a pressure vessel situation, the hoop stresses are the dominating one. So whenever you will have failure, you will have failure because of the hoop stresses. So you're going to have failure along the circumference because of the hoop stresses, not because of the axial stresses. So that's the only two equations we have for this chapter. So we can just do a couple of examples, and that's going to be chapter 8. So all you have to remember is axial stresses, which is along the axis, and hoop stresses, which is along the circumference of a pressure vessel. And the formula is PR over 2T. So this P is actually pressure. So P is our pressure, which is going to be in PSI or Newton per meter square. And then R is our radius, which is going to be in inches or millimeter or meters, and thickness, T is thickness of the vessel, and that's gonna be in inches also or in millimeter. So we can do one example. It's gonna make it more clear. So in this chapter we have two examples, 8.1 and 8.2. So in 8.1 it says we have a steel propane tank. So it's a propane tank, it has propane in it for the barbecue grill, and it has a 12-inch inside diameter. So the diameter for this is 12 inches, and the wall thickness is 1 by 8 inch, right? So it also has some thickness. So let's just say the thickness of the propane tank is 1 by 8 inch, and it also has, the tank is pressurized to 200 psi. So the inside pressure because of the propane tank is 200 psi. So all we have to do is that we have to calculate axial and hoop stresses in the wall of a tank. So we know that axial stress is PR over 2T and hoop stress is PR over T. So using these two equations, we can basically calculate the axial stress and the hoop stress. So thickness is 1 over 8 inch, which is going to be equal to 0.125 inches. So if you want to calculate the axial stress, pressure is 200 pound per inch square. This 2 is this, and then our radius is, this is diameter, so radius would be equal to diameter by 2, which is going to be 6 inches. So radius is 6 inch and thickness is 0.125 inch. So our axial stress is, right, axial stress here. So our axial stress is 4800 pound per inch square, which is psi. Similarly, we can calculate the hoop stress. Hoop stress is PR by T. Pressure is 200. Radius is 6. Thickness is 0.125. So hoop stress would be twice of the axial stress, which is 9600 psi. So the stresses in along the circumference, which is the hoop stress, is twice, which is higher. So whenever the failure is going to happen along the circumference. So if you imagine, if you keep on increasing the pressure, your both the stresses is going to keep on increasing, so it's going to fail in this direction. I mean, it's going to like explode like this. So whenever failure will happen in the propane gas, it's gonna like explode. You're gonna see crack in this direction, and that's how it's gonna explode. So you guys can do example 8.3. It's similar to example 8.1, and you can uh, find the axial stresses and the hoop stresses. Uh, so whoever needs more time, like whoever I have the emails for you guys, like whoever need more time, they can like come like last time. They can be here 8 a.m. like on Wednesday. Those who need more time, they can be here 8 a.m. So they're gonna start their exam 8 a.m. in the morning. So this is the air compressor. It has an internal pressure. So our P is 100 psi, and the internal diameter of the tank is 20 inches. So diameter is 20 inches. So radius would be 10 inches, and the thickness T is 0.25 inches, right? So we have to calculate stresses at point A. So at point A, we have to calculate the stresses. So this is along the axis. So this is axial stress. This is along the circumference. So this is a hoop stress. So vertical stress in this case is hoop stress, and the longitudinal stress. So this is along the length. So this is longitudinal. and this one is along the circumference, so this is hoop stress. So we can calculate. So exit stress is PR over 2T, P is 100, R is 10, 2 into 0.25. So that's what you're gonna get is 2000 psi, right? And hoop stress is PR over T, which is 100 by 10 over 0.25. You're gonna get 4000 psi. So that's our A part. So our B part is determine tensile force per inch length of the weld between right and left section. So we have to calculate the tensile force. So that's the force which is going to be applied along the weld. So usually, like if you don't have weld, then you're gonna have failure along the hoop stress, right? Because hoop stress is the highest stress, so that's where you're gonna have the failure. So if you wanna imagine the failure, if you keep on increasing the pressure inside, so ultimately it's gonna like crack and it's gonna explode, right? So if you keep on increasing the pressure, that's gonna be the crack, like because you have hoop stress higher, so this is how you're gonna see the crack, and that's how it's gonna like explode. But in our case, you have a weld also. So usually weld is the weakest link. Sometimes it cannot be, like sometimes it can be stronger, but usually it can be like weaker as well. So we have to figure out along the weld as well. So in this case, if the weld is the weakest link, then you're gonna see failure like this, right? So it's gonna like break apart if the weld is weak. Otherwise, it's gonna fail in the hoop direction. So along the weld, you have basically uh, axial stresses. So the question is determine tensile force per inch length. So first we'll calculate the force, and then we'll divide by the length, so we'll get force per inch length. So this force per inch length is actually the same in our case. For example, when we had a simply supported beam, for example, and when we have a uniformly distributed load, this W was given in pound per inch, right? So whenever I gave you some value of uniformly distributed load, I gave you in terms of pound per inch. So this pound per inch, this W is actually called force per inch length. And we can calculate the total resultant force by multiplying the length, right? We can calculate the resultant force from this pound per inch length by multiplying the length. This is what we were doing before, right? So if you want to calculate W, you're going to get force divided by length. So you have to calculate the force and you have to divide by length. You're going to get force per inch length. So let's try to calculate the force for the in this case. So we have to basically calculate the force. So in this case, we're talking about external load, right? This is going to be external load, which is force per inch length. So we know stress is force per unit area, right? But in our case, stress is pressure. So pressure is force per unit area. So pressure is basically pressure is equal to applied stress. You can say applied stress. So pressure is stress. This is our pressure. So pressure is actually uh, the unit of pressure is psi, and unit of stress is also psi, right? So pressure is basically stress. So we have to convert pressure into force. So how we'll convert pressure into force? By using this formula. So force is equal to pressure into area. And what is the area in our case? The area would be pi r square. Why it's going to be pi r square? So if you, I'm going to draw, I'm going to cut a section and I'm going to draw a cross section here. So if you draw a cross section here, this is all the pressure. This is the gas, and this gas is applying forces along the, so this is actually pressure, right? And if this is our diameter, so we have to calculate the area, and area would be pi by 4 d square, or the area would be pi r square. So that's what I have done. So pressure is 100 psi, pound per inch square. Pi is 3.14, and radius in our case is 10, right? Whole square. So you're gonna get force, which is 31416 pound. And from here we can calculate force per unit length. So which is W naught, right? So this is going to be circumference actually, because you have an external force which is being applied along this entire length, right? And this entire length is actually pi d, which is the circumference. It might be a little confusing, but all you have to know is how to calculate axial stress and the hoop stress by using the formula. So the force is 31416 pounds over circumference is pi d, 31416 pound over 3.14 into d, diameter is 20, right? 20 inches. So the final is 500 pound per inch. So, you have to just figure out why we have used pi r square and why we have used pi d here.